pleasure to introduce the Student's Choice speaker, Dr. Michael I. Jordan, naturally introduced by a student. So Dr. Jordan did his PhD in cognitive science at UC San Diego under the advisement of David Rungelhart and Donald Norman. Afterwards, he joined the Department of Brain and Cognitive Sciences at MIT before continuing on to be a joint professor in statistics and EECS at UC Berkeley. Dr. Michael Jordan is an all-star of artificial intelligence research. His work has earned him the John von Neumann Prize and a membership of the National Academy of Sciences. In addition to his many accolades, Dr. Jordan is an avid drummer. If you are lucky, you may find him and his colleagues jamming out at a STEM conference near you. Please give a warm welcome to Dr. Jordan.
Thank you. That was the best introduction I've had in a long time. I appreciate that. So it's nice to be here. Typical Seattle weather. It's nice to be in an applied math venue. I kind of think I am an applied mathematician in the sense of I like to do mathematics for the applied problems of the day. And so that title actually is more about what are the problems of the day. And I want to say something about what they are because everyone's talking about it. The only thing I would correct there is I don't really think of myself as an artificial intelligence researcher. I'm really a statistician, fundamentally, more on the math side. But I want to talk about what AI is and kind of why I don't think of myself as an AI researcher. So you'll see some of those other words there. They'll hint at what I think I really am. I will do math here. I'm going to get to some theorems, and I'll have some if and only if statements and so on. So that'll probably be the second half of the talk. The first half will be more why are we doing what we're doing. And I'm doing that partly because it's a hopefully somewhat broad audience, and especially the students should know or think a little bit more about why they're doing what they're doing. It's not just to build our careers or to publish papers. It's some nice social impact. And this is an era where that seems to be particularly worth discussing. All right. So first of all, this emerging field, if you want to call it that, was really never called AI. That was an old terminology used in computer science departments that was kind of embrace everything. It was often called machine learning instead, which was really kind of statistics dressed up a bit with computer science ideas. But really, the right way to think about it, it was not academics at all that drove this. It was really industry problems that were being solved. And so this is my little short history. Already by circa 2000, if you go to a company like Amazon here in town, or you go to Alibaba in China or others, there was vast amounts of data. Now, data on what? Well, on things like supply chains. Amazon, I think, is currently serving about 1 billion products to hundreds of millions of people. And can you imagine the supply chain that's behind that? It's shocking. And to make that supply chain work, it's a stochastic control problem. You're sensing all kinds of variables, like what ships are in the ocean, how long it's going to take them to get across, what parts are being built here or there. And you then have various control knobs, and you're trying to make that thing work so there's high throughput. So it's the world's largest stochastic control problem, ever conceived of. And you can imagine, you're not hearing?
Yeah, you can move the mic up or you can turn up the gain. It's just a little quiet.
I could probably turn up the gain, yeah. Thank you for saying that. Actually, I have no gain control here that I see. It's probably onto the device. I can also move it out. Oh, you just did it. That's good. Okay, not too much. Thank you. A little too much. As a musician, I know what that phenomenon is. All right, now's that better? All right. So, they were running these big stochastic control problems. So, they were taking in vast amounts of data and they were making predictions about what's going to happen tomorrow so they could, have supply. And they ran these algorithms. And what algorithms did they run to do all this prediction? It wasn't linear regression. That wasn't going to work. It was what was called random forests. That was developed by my colleague Leo Breiman at Berkeley. And random forests work great. And they're probably just as good as neural nets. They were the technology of the day, just different. Now to run them, you needed huge amounts of data. They had that. And then you needed lots of compute. And so they had to do that. So you could run these algorithms on a single laptop at that scale. So they put together tens of thousands of computers so they could run these random forest jobs. And they had a server, a whole program set up to do that. And it really worked. That led to Amazon becoming Amazon. All right. That was the genesis of the cloud, by the way. They did it so well that they had way more capacity than they needed, so they started selling to other people, and that's the cloud. So it came from machine learning. All right. Now, and moreover, I know about this because I would go visit a little bit and talk to them. The algorithms are the same we have now, gradient-based algorithms at very large scale with large amounts of data. It just wasn't human data. But if you kind of looked at the solutions it would find for logistics problems, they were interesting and surprising to logistics experts. Okay, so not that different from where we are now. These machines coming up with things that we found interesting and surprising. How did we get there, though? Well, the next 10 years, these companies still realized they had lots of data about transactions, not just about ships in the ocean and all that. What are transactions? Well, it's human interactions. Human preferences are being expressed. So they could make recommendations based on that. If you bought some stuff and you're similar to me, then maybe I should buy that stuff and all. And that led to recommendation systems. Same hardware, same everything, same algorithms, just different data sets. And it was hugely important. Both of these had, billion-dollar effects on the economy. Okay? And it was never being called AI, and it was never being talked about in the New York Times. The third era was when people realized they had a lot of data, not just about human transactions, but about speech and language. And they could pump the same data or the data into the same kind of algorithms, gradient-based algorithms, and then do some smart versions of them. And, suddenly you can now predict the next word in a sentence very well, and you can do things based on that. And that's what we have now. And then suddenly there's, all hell is broken loose with the journalists talking about it and people talking about it. Now, maybe some of that's warranted. It will change business models. It'll change the world in some ways. But it's more of a continuum from where we were 20 years ago than suddenly a brand new thing. It's definitely not a brand new thing. Okay? The ideas are not. Now, whether you agree with me there or not, I do want to kind of highlight that I don't think this is about just pattern recognition algorithms scanning vast amounts of data and predicting the next word in a sentence. That's pattern recognition. Really, we're trying to build systems that are systems, and that's best thought of at the level of many, many people. Okay, so a transportation system is a system that uses data and makes decisions, and a finance system is one, a commerce system, even an entertainment system is one. And these are all markets. Okay, they're not just systems, they're markets. And they have data being flowing around as in conditioning the market reactions. So it's a new kind of market. It's not a classical market where there was just a few simple rules, and then people would think in that context and play the game. Now there's all this data being conditioning the market. So that's a brand new academic discipline as far as I'm concerned, and I think that's what's having impact on the real world is these kind of markets. All right, and so historically, we've seen every 50 years or so, a brand new engineering field kind of eventually emerges. So let's just look at the history of, say, chemical engineering. It arose as a real discipline in the 40s and 50s. The name was used a bit before that. But before the 40s and 50s, there weren't large numbers of factories out in the fields. Okay? But there was already quantum mechanics. There was already fluid mechanics. So you could understand what happened in a test tube when you put some molecules together extremely well. Right, but the idea that you could put those molecules together at vast scale and make products like chlorine for swimming pools or polymers, things that have changed our lives, medicines, that was a dream, and that was hard. And so people tried, and some of these factories just didn't work. Most of them didn't work. They didn't produce the product, or they were not economically viable, or they blew up and killed a lot of people. All right. So eventually a field emerged called chemical engineering that built on all that experience, but added some more math and, did some new thermodynamics at scale. New concepts were needed. Same thing for electrical engineering. Before there was electrical engineering, there were Maxwell's equations. So there was a deep understanding of the phenomenon, right? But it wasn't clear how to take that understanding and electrify a city or bring power into a house and not burn it down or build communication over those waves that Maxwell gave you. And so people tried, and they built things, and they were helpful in some cases, and they scared a lot of people. People were afraid of electricity. But eventually, a field emerged called electrical engineering that, again, made this into an engineering field. And electrical engineering is not just engineering of electrons, right? It has its own mathematics, its own concepts. So I think that's what's happening now. We have some proto kind of ideas of how to do decision-making at a very small scale, like one individual in a certain situation. We have data analysis of a particular data set. We make particular inferences. So we kind of have like the molecules a little bit. We don't have anything like quantum mechanics or a wave equation. But we have enough to think that there's kind of something there. We know how to do gradient descent. So we now try it at big scale. We build factories. And some of those factories are working and some of them are blowing up and we don't really have much of a clue. So a new field is emerging. That's what I think is actually happening. AI is not some brand new technology unleashed and we're watching this powerful giant, devour things. It's gradient descent, properly managed, can do some cool things, but it's a whole engineering discipline with all of the issues around that. Like when you bring electricity in a home, what makes it not burn down? Well, there's Underwriter's Laboratory that checks things. There's all kinds of standards and all that. And it wasn't easy to do that. Okay, so same thing here. It's not going to be easy to do any of this stuff. All right, and now, unfortunately, this term AI got affixed to this whole emerging engineering field. Okay, and so AI, was John McCarthy's term. And in his view, he was almost a philosopher. Like, how could you put thought in a computer? What would that mean? And we don't have thought in a computer yet. We have statisticians, automatic statisticians, if you will, that can do pattern recognition and come up with some cool algorithms. All right. Really, what happened was what Doug Engelbart called intelligence augmentation. Things like search engines arose, recommendation systems, and all. So they're taking vast amounts of data. They themselves are not smart. A search engine is not smart. It just indexes the web, arguably not smart, but it makes all of us way more smart, as does a recommendation system and so on and so forth. So you can think of it that way. Is really what we're trying to do is build systems that augment human capabilities, not replace human capabilities. So I think I would go with him instead of him. But anyway, in the meantime, I think, again, it's not about a single computer and a few users. It's really about the collective set of people engaged with algorithms. So this 50s perspective of McCarthy was the one that you see in the newspaper, and I'm going to turn to other material right after this, but I just got to say this clearly. If the goal is to understand human intelligence, that's a fine philosophical goal. We don't have it, and it's not even really clear what it means. The business model behind that is not clear either. Oh, does that mean, I see, you've been able to take a computer and make it be just as good as a human, even better than a human? That means I can take out the human and put it in the computer and everything will be better? Okay, that's the naive thing that you see out there. That just seems wrong. And secondly, why do you think you understand intelligence? So is an ant colony intelligent? Well, yes, arguably, so they can build a little mound, they can bring food around, they can do those things, and no single ant has any clue what they're doing. All right. Okay, we all know that example, but also the economy. There's an economy. It's like a colony, if you will. That brings food into Seattle every day, and enough food is brought. There's not too much, not too little, and it works no matter what the weather is. It works, for thousands of years, and in cities, villages around the world. It's called a market, and the market dynamics and economies have their own rules and they have their own intelligence. They're adaptive, they're robust in ways that these AI systems just aren't. So why don't we study that kind of intelligence as well as the human kind of reasoning modus ponens kind of intelligence? All right. So again, the AI dialogue just doesn't encompass that. It says, well, we got AI, we got supercomputing. Oh, we got to worry about the ethics of replacing human beings. But we don't think about what is the market we're creating? How do people engage with these systems in an overall collective? All right. So that's maybe enough. And now I think you know what my counterpoint is going to be. It's somehow obvious to a social scientist or an economist that intelligence is as much about a collective as it is about the individual. And if we're going to design systems, the goal should be expressed at the level of the collective, not the level of the individual. So if we're designing a system to help with transportation that makes autonomous decisions about where cars should go or provisions or whatever, the overall goal should be good throughput of that system. It shouldn't be that some individual drove particularly well. All right, and similarly for finance, similarly for commerce, and so on. So I hope these maybe agree. These are kind of the problems of the era, is how do we build these collective systems that are brand new, include humans and computers in new ways. Now, if you ask people in machine learning, do you work on this? Mostly they say no, but then they say occasionally, well, there's this thing called federated learning. Isn't that an example of this? So federated learning is a model in which you have a global statistician like Google who wants to collect vast amounts of data so they can train some algorithm like a speech recognizer. And they don't have a lot of speech data in-house, but they have all these cell phones out there they can collect data from. Okay? Now, eventually people are going to not be happy to have their data taken, so Google says, well, we'll provide privacy guarantees. We'll also compress the data, blah, blah, blah. And now the question becomes, can you learn from that? And they wrote papers about that and called that federated learning. All right. So it's a good problem, nothing wrong with it. You should work on it and all. But I hope you can sort of see this is not the real problem. The real problem is, why should people be incentivized to be in that world at all? Why should they allow their data to be taken in that way? Why shouldn't they expect something more in return than just that Google produces a good speech recognizer? What is the economic model underlying all of this? All right. So a broader framing is that these nodes at the edge of these federated learning graphs are not just nodes, they're people. And people are not just producing data that they don't care about, like my location in this moment or what I ate yesterday. I'm probably, I put my articles that I write, or I'm doing it on my cell phone often, or some poem I wrote, or some song that I've written. Not just me, but everybody is doing this. And that's going to happen more and more. A lot of our creative lives is going to be taking place on these platforms, and we're going to be sharing it in all kinds of ways. That's not just fodder for some big company to grab and then monetize it and take all the money. And that's just a broken way to think about our economy. All right, so there should be benefits coming. And so now if we get more into the what should academics do, well, you should be both an economist and a statistician and a computer scientist. Right? What does economics bring to this? Well, they bring in this field of mechanism design. This is a game that's being played among many players who are opting in, opting out, deciding and making decisions, and then there's a result. What games should be designed? What are healthy ones? How could that be learning aware so that those games are reflecting data and adapting over time like a good market should? What are the algorithms that will do that? So those are brand new fields. Those really don't hardly exist. Let me be really concrete before I turn to more of my mathematical work. This is a company I'm involved with. It's called unitedmasters.com. It's about music. And so briefly, the idea here was that this came from Steve Stout, who's a friend of mine and a legendary hip-hop producer, very well known in the music world. He is the CEO of United Masters. This came from looking at the data of music. So all of us listen to it a lot. It seems good things are happening with music. If you are aware, though, what's really happening, it's not so good. So more songs are being written today than ever before in history. That sounds good. More songs are being listened to than ever in history, right? And if you look at it, 95% of the songs being listened to today in the United States are songs that were written in the last 6 months and written by people you never heard of. So that may be a surprise to you. You may think everyone's listening to Beyonce or the Beatles, depending on their generation. That's just not true. It's all these young kids that's their life. They're listening to the latest song and the coolest song, and they're transmitting among themselves and all. There's a whole thing going on. The problem is none of them are making any money from this. There's no jobs to be had. So it's something you do from age 16 to 20, and then you're out of luck. All right, so that seems weird. Isn't somebody making money? Well, Spotify's making some money. They could probably make a lot more, but they're making a lot of money, but they're not giving it back to musicians. They're giving it's 0.0001 cents per play. It's insane. All right, so it's not a working economic model. For music, one of our great cultural things, it's being broken. Okay? All right, so anyway, United Masters aims to fix this. It is working. It's a three-way market. There are musicians who produce, there are consumers, people listen, and there are brands who want to partner in relationships. So in particular, the National Basketball Association is one of the partners here. The NBA, if you go to the website and you watch a clip, there'll be maybe music behind it. And 2 years ago, that was Beyonce or Kanye West or whatever, and they would get paid. Well, actually, the record company would get paid whenever you listen to it. Now, if you go and listen, the artist you'll hear is a United Masters artist, probably a 16-year-old. And when you listen to that music, they get paid. Okay, so that's two sides of the market. And now it's a market. It starts to do creative things. Other brands look in and say, oh, I see those musicians are being listened to on the NBA website and they're popular. I want to buy in. I'm going to reach out to that musician and ask them to write some songs for me. Nike did that. FIFA's involved. So brands can be good. They can be sources of income for people who are doing creative work if you connect up the market and structure it appropriately. It's not just a handout. It's not anything it's a real working market. 3 million young musicians are on this platform, and many of them are making real money, what we might even call a salary. Okay, they're not going for billions of dollars like Beyonce, but they're making working money. So I think this is a good example of what we should be aspiring to. And so behind this, of course, there's a lot of data analysis, but there's a lot of market analysis too. Market analysis in the sense of what are the incentives? How do we make sure it's fair and to long tail? How do we make sure there's kind of recommendation, connections being made? It's a matching market. There's all those kind of things are happening. So it's microeconomics ideas meets statistics ideas under the hood here. Okay. You can obviously imagine this not just in the U.S. You can imagine this certainly in Brazil, certainly in Africa, certainly in China. You can imagine around the world creating jobs. And you can imagine not just for music, you can imagine for other kind of arts. All right, so in Silicon Valley, you don't hear much good discussion of things like this at all. It's all about how do we monetize with advertising. But they do occasionally use words like the creator economy. And I think that's right. This is an example of creator economy. All right. Let me go briefly here. Just recommendation systems, are a powerful economic concept. If you buy some things, they recognize a pattern and they'll recommend things to you. You will probably be more likely to buy them. So, books famously with Amazon and, films and so on. And so it's a pattern recognition system, and it makes, pretty good predictions about what you're about to buy or might buy, and it helps the economy. But just a prediction system alone, is that somehow enough? Is that like really doing good commerce? Well, not really. So if you use it to recommend things where there's no scarcity, then it's kind of straightforward. Like if I recommend movies to people, and I happen to recommend the same movie to 100,000 people, which happens, I'm sure, all the time at Netflix, and everybody buys that movie, I just copy the bits. Same thing for books. I can copy books really quickly. What if you recommend things like restaurants to people? It's a good in the real world that you can't copy. You can't suddenly copy the restaurant 5 times, right? So you create congestion, right? Similarly, if you recommend streets to drivers, here's the fastest road to the airport, and 100,000 people get that recommendation, you created congestion. All right, so an economist would say, of course. But amazingly, Silicon Valley, the people that build these platforms and these systems don't think this way. And once they realize they've created a problem, they say, we could have fixed the problem. What we're going to do, it's a load balancing problem. I'm not going to ever allow 10,000 recommendations for a restaurant to go out. I'm going to cap it at 100 or 10 or whatever. Okay, that's what they literally do. Is that a good model? Well, I hope you can see how silly it is. Okay, so think about, say, college admissions being done this way. A lot of people apply to UW. What if I just say, well, I'm going to cap it, the first 100 get in and no one else gets in? Okay, all the preferences on both sides of the market, we don't care about that. We're just going to cap it. All right, so it's a terrible economic idea. And so a better economic idea is just actually literally do economics, to build some matching markets that have adaptive data flows like we somewhat do with college admissions. Now, college admissions is a good example because it kind of works at some level. It's not great, or kidney exchanges and these kind of things are famous. But what's wrong with them? Well, when I'm applying to a college, I have to write down a preference ordering on all the colleges. Okay? That's a huge effort if you have kids, All right? And the colleges have got to make lists of all the criteria, and it's quite a mess. And then a matching algorithm runs that is optimal in some sense. And people got Nobel Prize for that. Right. Now think about doing this in all kinds of other real world domains of the kinds that we have access to. I'm not going to be able to write down a list of preferences of everything in my life. Certainly if I go to Shanghai and I've never been there before, I can't write down a list of preferences of all the restaurants I want to go to. Okay. So that just can't work. How's it going to work instead? Well, lots of other people have been to Shanghai. They found some preferences. If they're similar to me, that should feed over. So I should have things like recommendation system, but in the context of a market, where now I'm available to the other side of the market, like in college admissions. I say, I want to go there. The other side of the market looks at all the applicants, and adaptively, it's all being adjusted. The preferences are learned from experience. Okay, so that's something that microeconomics people have not done. All right, anyway, so I used to think of myself as really a statistician, and then I learned about this terminology, machine learning, and I looked at it, and it looked like to me it was just statistics, but then I recognized there were principles from this field called computer science that were allowing it to be done at scale and, in ways that I couldn't conceive of in my statistics classes. That was good. And so I started saying, yeah, I'm a machine learning person. At some point, though, as you can see from my language, I realized that machine learning is missing economics. It has no model of interacting agents who have preferences and utilities and incentives and all that. Nothing. You see very little in machine learning. And many of the problems of machine learning come about because of that. So I said, okay, we should bring in economics. Does economics already have connections to statistics and computer science? Well, yeah, it does. Very healthy ones. Statistics meets economics. That's called econometrics. Econometrics is kind of mostly time series analysis and causal inference. It's pretty good. It's mostly about measuring the economy, and it's mostly for macroeconomics. I'm caricaturizing a bit, but and it doesn't have hardly any kind of algorithm content to it and building systems. That's not econometricians. What about economics meets computer science? Well, that's an existing field. That's called algorithmic game theory. It's got cool algorithms for doing mechanisms, auctions, and all sort of things. that have computer science flavor and economics flavor, but there's zero statistics. There's not, let's run the thing for a while, collect some data, improve it. There's no feeling of that. All right, so I hope you can sort of see that this is kind of a nice academic triad to sort of solve these real world problems. And this came partly from me not just being an academic, but being in industry. I spent a little time at Amazon, a little time at Alibaba and stuff, and I perceived that when really challenging problems were being solved, that some service was being made to provision to real users and real buyers and producers and consumers, there were people from all those disciplines contributing to an actual effective solution. And not just those disciplines, like for example, operations research peoples were often critical, and chemical engineers and others. Okay, so with that as background, now you have a little sense of why I work on what I work on and why I don't think I'm an AI person. I don't like the terminology, but whatever. But we do have some kind of interesting real world problems to be working on. And so what do you work on then as a researcher? And here's a list of some of the things I've been working on the last few years. I'm going to pick a subset of these to kind of give you like 5-minute little vignettes to get, show you some real examples, real theorems. I'm going to talk a little bit about exploration and incentives, a little bit about information asymmetries. That's one of my favorite phrases. A little bit about uncertainty quantification in an economics context. And I'll skip over some of the others. The one at the top, though, I decided I'm going to spend a few moments on that one separately because this is an applied math department. And you know a lot about algorithms that are dynamical systems, right? So in machine learning, over the last many years, we've become increasingly good at finding optima in high-dimensional problems, gradient-based methods. Not just good in practice, but also good in theory. We have algorithms we have lower bounds, we have upper bounds, they're tight. We have dimension dependence on these things. We can do this for convex and non-convex problems. And when I say we, it's like, 5,000 of us working on papers on this. So it's a real success story. In real life, though, you don't often hope to find optima. That's like if you had a centralized solution and everybody was told command economy. In real life, you expect to hope to find equilibria, where no one can kind of make unilateral improvements, things like that. Are there algorithms that find equilibria? There are, but many fewer than there are for optima. Okay, the ones that find optima pretty well, like gradient descent or stochastic gradient, it finds optima really well in high dimensions. If you try to find equilibria with gradient descent, you mostly diverge. It's a known fact. There are algorithms that are improvements on like extra gradient and proximal point that will find equilibria. There's much less known about them in high dimensions with non-convexities and so on and so forth. So there's kind of a lot of open problems in that second part. But really, even more interestingly, it's about dynamics because the real world systems that I'm interested in are always changing and over years and so on. And so can you find dynamical systems that will converge to healthy equilibria over time robustly and keep tracking those things and not go unstable? Okay, huge number of open problems there. So let me just give a little sense of the things that we've done to kind of get our arms wrapped around some of this. So this is a subset of another talk, and I'm going to put in like a 5 or 10 minute little parenthesis here. This is a talk I would have given if I'd come here 2 years ago, and then I got off on all this economic stuff. But before I was doing that, I was doing dynamical systems, variational Hamiltonian, and symplectic perspectives, and I want to give you a little flavor of that. This is a subset of that talk, bigger talk. And so this is on variational Hamiltonian and symplectic perspectives on acceleration, which is a particular way to think about optimization algorithms that turns out to be extremely helpful. This is work with Andre, Aisha, and Michael. So just to kind of now start to turn to a little bit of mathematics. So you all know what convex optimization is. Here's a convex function on, say, Euclidean space. You all know what gradient descent is. And you may or may not know that this has a convergence rate of 1 over the number of iterations. If I weight that number of iterations, I'm going to be in a ball of size 1 over k of the optimum. There's a unique optimum here. All right. Now, it was understood at some point that gradient descent, that rate of 1 over k was pretty good, but not great. And there was a lower bound at some point. So this was due to Arkady Nemirovsky and Yudin in Soviet Union. They proved a lower bound for any gradient-based method. So this is a complexity result of 1 over k squared. Okay? You can't do better than that if you're only using gradients. So that was pretty cool. Now, gradient descent is 1 over k, so there's a gap. And the question for a while was, is just a bad lower bound. Maybe the lower bound is really 1 over k. Or maybe there's some other algorithm that goes faster than gradient descent. And the latter seemed kind of not so plausible because gradient descent, is taking the steepest descent direction. If you're trying to go downhill, what could be better than that? And it maybe came as a surprise that Nesterov invented this algorithm down here called accelerated gradient. And it has a rate of 1 over k squared. And it's just 2 equations instead of 1. So the first equation kind of does a gradient step, but it does it on a different variable, sort of a separate variable. And then it takes a convex combination of the last 2 y variables to form the next step. All right, so it has a little bit of a momentum flavor, but what's amazing is it's provably faster. And this then kind of, for the last 30 or 40 years in optimization, became quite a cottage industry. People took gradient methods that were well understood in many, many domains and then found accelerated versions of them that were faster and reached lower bounds and have had a huge impact. Nesterov and Nemirovsky just won something called the World Laureate Forum Prize in mathematics this year, quite deservedly so. They're not so recognized outside of mathematics. They're really applied mathematicians in my view, and they're the first to win that kind of prize. All right, so that's fantastic. But it was never really clear how to understand these algorithms in some general sense. What is the acceleration phenomenon? Why is it arising? All right, and so the work we did was we found explanation for why acceleration arises if you go into continuous time. It's not a discrete time phenomenon. You can't really understand it there. You can write some equations that sort of capture aspects of it, but the understanding comes in continuous time. All right, so how did we go into continuous time? Well, we wrote down a Lagrangian. All right, so this is a continuous time Lagrangian. It's a function of the position x, that's the optimization variable. We also have a velocity, so we can get some differential equations. And we have time. And we have a Lagrangian there that's time varying. The first term is a Bregman divergence. It's a Bregman divergence, which is kind of that, that little red thing there is the Bregman divergence between x and y, if you've not ever seen this before. There's an auxiliary function h. It's a Bregman divergence between where you currently are, x, and x plus a time-shifted x dot. So it's a little bit like look ahead. Alpha, beta, and gamma here are just degrees of freedom that give us a space of algorithms and not a single algorithm. They're just diffeomorphisms. We take that Bregman divergence and we subtract from it a time-scaled version of f. This is the thing we're trying to go downhill on. So think of f as a potential function and think of the Bregman divergence as a kinetic energy function. In fact, if h is quadratic, the first term just becomes 1/2 x dot squared, literally the kinetic energy. So we've got a time-varied Lagrangian. And with a Lagrangian, of course, you do what you do with all Lagrangians that Lagrange and Euler told us what to do. You optimize them as an integral over paths. And the path is characterized by the Euler-Lagrange equation, which is just a system of, it's just an ordinary differential equation. You take some partials of L and this is kind of like setting all the partial orders equal to 0. And if you do that, you can do it on the back of an envelope. You will get this master differential equation. It's a differential equation for doing optimization in continuous time. Okay? It is a second order equation. Like we saw with Nesterov acceleration, you need 2 equations. 1 is not enough. It will tend to go down and come back up. It will oscillate. That's good. That makes you go faster to going downhill. If you're a physicist, that's not maybe a surprise. It's time varying. It's got a time varying damping sitting right there. And it's also got a bunch of geometry sitting right here. And all that geometry comes together to make this thing have a lot of nice mathematical properties. This thing is equivariant. And what that means is that if you choose different speeds you want to go downhill on, you will put different alpha, beta, and gamma functions in when you do that. And what it'll happen is that it'll pop out the same exact path and you'll just move faster or slower along that path. So we've discovered a way to characterize paths which are good, and I don't care what speed you go, that's just what clock you use, and it doesn't really matter. Okay? And then we were able to prove a single convergence result for all of these algorithms once with one Lyapunov function. So that was Aisha Wilson's work. All right. So in this model, we've extracted out the geometry. We've discovered something about a Lagrangian that makes things go quickly downhill, right? But we kind of made the phenomena go away because now you can go arbitrarily quickly. If I say I want to go exponentially fast, I can put in alpha of t is just equals to 1 over t, right? I put it into the equation, I get a differential equation. And if I were to solve that in continuous time, I would zip along that same exact path. I would just go exponentially fast for the outcome. Right? In continuous time, that's possible. But we know there's these lower bounds in discrete time. You can't go that fast. So what happens? What breaks? All right, and so that would turn out to be the secret. It's a phase transition in the ability to discretize certain differential equations. For certain rates, slow rates, you can discretize them stably up to some point. Beyond that point, it's impossible to discretize them stably. Okay, so it's the acceleration phenomenon can be thought of as a phase transition in the ability to discretize certain differential equations. All right, so anyway, that was, we thought of these as mysteries for a while. This is an older slide about 5 years ago, and then we finally resolved those mysteries. And we found one particular way to do this with symplectic integrators. If you're a numerical linear, or if you're a numerical ODE person, you know about this. And so we took our Bregman Lagrangian, we got an ODE, we used symplectic integrators as our integration method, which we knew had some nice properties. And then we got an optimization algorithm. So it was just a chain of mathematics leading to an optimization algorithm that had provable properties. All right, and then we tried that on a bunch of problems. Here's a particular problem. It's a high-dimensional quadratic. And you can see it's going pretty fast. We know what that rate is. And you can see that it oscillates. It goes up and down. We know that's good. And Nesterov's algorithm, by comparison, if you turned the step size down a little bit, you were less ambitious, Nesterov and this method would track each other exactly. So it recovers Nesterov. But on this slide, you see that if I turn the step size up faster to go faster, Nesterov goes unstable. And this method does not. And if you know about symplectic integrators, these are structure-preserving integrators. They will preserve things like energy and momentum. And that means they're a stable form of discretization. And that stability means you can push it faster. You can go faster. That's the connection to acceleration. Okay, so finally we wrote a paper that did all of the applied math of this. This is in one of the physics journals. We proved that symplectic integration will have this phase transition we talked about. We also proved, we did a backward error analysis. So we proved that all the errors were under control in the discretization. So that paper kind of is the final nail in that coffin. All right, and then this, I usually don't do this, but this is advertisement for a whole line of work. So after that paper, we did a whole bunch of other papers because now we had a Lagrangian, we had continuous time, and we knew how to integrate. And we could do that now for non-convex problems. We could do that for stochastic problems. We could do that for extra gradient problems with minimax problems and so on. And so it was just a lot of fun for like 5 years in doing all those papers. And so if you want to look on my publications page, here are some of the highlights along the way on those papers. Tatiana Chavdarova, this last paper is one of my favorites. So it's last iterate convergence, that's hard to achieve, of saddle point optimizers using high resolution differential equations. So high resolution is another technique beyond or different from symplectic, which we found very useful. Okay, all right. So looks like I'm about halfway done, or a little more. All right, let me pause for a second. Any questions? So I can just take a breath. Clarification type questions? Okay, so let me go back to the main thread of my talk. I'm going to be doing, question, please. Can you just distinguish a little bit more between equilibria? Is it like just any stationary point? Or what makes something like? Well, what do you mean by stationary? It's not stationary points. Yeah. Okay, so stationary points are an optimization terminology. Like a saddle point in optimization is something you don't want to hit, right? It's a stationary point, but you're kind of stuck there for a little while. In multi-agent game theory kind of problems, a saddle point is a good place to be. That's the place where I'm as happy as I can go because I want to go down, and you're as happy as you can go because you want to go up. We're both as happy as we're going to get. Okay, so saddle points are generically kind of good in the equilibrium world. And now if you think about the vector flow underlying, say, just a classical saddle point, it's a bunch of concentric circles. The vectors are kind of chasing themselves around. All right, and in fact, that's a nice one to think about for a moment. Imagine I just gave you a two-dimensional vector flow. That's a circular. It's got curl, just a bunch of vectors flying around. And that's my vector field, and I ask, do something with that. And you say, well, should I optimize? It makes kind of no sense. I could follow the vector and I'd go around in a circle. I'd have a limit cycle. No, you shouldn't optimize. So you should probably find the thing in the middle. That's a fixed point. All right, and maybe the fixed point is mean. Well, in fact, it is the saddle point, the Nash equilibrium. So you do want to find that point. How can you find that point if you're just out there in high-dimensional space somewhere? Well, you might say, well, I can just do gradient methods. I'll follow the flow. And now, not only will you not go, it's even worse than you will go around in circles. You won't go around in circles. What will happen is you start on a circle, and here's my flow, and it's tangent to the circle. So I'll take any finite step will go outside the circle. And then I do that again, I'm outside the circle, I will actually spiral out. All right, so gradient methods just don't work, and you have to now do some work on it. So equilibrium finding is really fixed point in algorithms, and there is an older literature on fixed points, but now, just like we did with gradient methods, needs to be brought back into the modern world. Okay, so back to the main thread of my talk. I'm now going to do a couple of vignettes, each one of which bring economics into contact with data analysis. Okay, again, I'm arguing that's kind of what AI is about. So this is one good example. Contract theory is part of economics, and obviously statistical is part of statistics. Stephen is now a young professor. He just started at MIT. Michael's at Stanford, and Jake is at Chicago. They were with me at Berkeley. All right, so briefly, what is the theory of incentives? I'm not an expert. I learned about this the last few years when I decided I would need to learn economics, so I started reading books. One of the main forms of mathematics underlying microeconomics is game theory. You probably all know about that. And in game theory, I've got multiple agents, and they're all choosing some action, and maybe they choose them simultaneously, and I get a classical game. I have a little table. Or maybe they choose them one after another, and I get a sequential game. But in any case, actions are being chosen, and then an outcome is realized. And the agents might be zero-sum, where this agent wants to go up and this agent wants to go down, or they may not be zero-sum. Okay, so that's game theory. And a lot of economists use game theory to model the world, just like an OD person might use differential equation to model an ecology or something. And so they write down a game and they say, is that what we've seen in the real world? And in particular, the solution of the game might be a Nash equilibrium. Do we see that Nash equilibrium in the real world? If we do, it's a good model. As an engineering-oriented person or a statistician, I often want to go backwards. I want to say, here's an outcome I'd like to see in the real world, that everybody gets paid and it's all fair and all that. Can I design a game that will deliver that outcome? So it's inverse game theory. And in economics, inverse game theory is called mechanism design. Okay, just the word. And there are many branches of mechanism design. One of them is one you're all aware of. It's called auctions. Okay, so an auction is a game. Okay, I tell you, you come in and you have a number of plays, which is to write down the value for something and make bids. Those are your plays. And after it's all done, there's an outcome, and someone wins and someone loses. Now, I would like to design an auction that gives a favorable outcome, that everybody had, felt treated fairly, and there was revenue made from it and all that. And that Nobel Prize was given 2 years ago for that. Okay. Do we want to have auctions as our main mechanism for bringing out human values into problems? Probably not, because auctions require a lot of work. And you got to write down all your preferences, and you got to make bids and all that. Is there another branch of incentive theory? Yeah, and it's called contract theory. And now you all know what it is. A contract in economics language is a menu of options. You have a service and a price, a service and a price, and there's many of them, right? And this is a new notion, sort of not back in history. There was not lots of these. And it came into prominence in the 1980s. And I remember this era. The airlines were all tanking. All of the national airlines were going. There was no business model. You couldn't make money with airlines, and they were all going away. And so there were a few low-cut airlines that came in and tried to displace the Air France and so on, British Air. And they did for a little while because they had these low prices. Because the problem was that Air France and British Air there was so much cost, they were like, the price was really high, and no one was flying. So these airlines come in, they bring the cost down, so everyone's flying now, they make a lot of money. Right. American Airlines famously hired an economist and say, how can we help? How can we fix this? And this guy, he was a guy, said, what you need to do is you need to have a menu of options. What are your menu? It's like something called, he invented it, business class and economy class. All right, what is business class? For the young students in the room, you probably don't know about this, but there is this thing called business class. And you pay a lot more money and you get a little glass of red wine and you get to be first in line and you get a slightly bigger seat. And unbelievably, there are people that are willing to do that, and they feel so proud of themselves and everything. And so they pay a lot, and the airline makes a lot of revenue from them, and they're happy because they were willing to pay a lot. And in the meantime, there's lots of other seats that are offered at economy fare. and the students come on and they pay that much cheaper rate. They have to sit in a tiny little seat on, but they're happy. They walk past the business class people feeling so good about themselves. They paid so little to be on the same airplane as these guys. So everybody's happy. That's called social welfare. And there's high revenue. And that saved American Airlines, and it then saved all the airlines. And now we love to complain about the airlines. We don't like all of this. But the fact is, if we didn't have all this, we wouldn't have airplanes. All right, that's one of the interesting things about economics, is that we don't like it, but it offers all these possibilities for us. All right, so does construct theory kind of solve the kind of problems that I think are emerging? No. So here's a good example. Clinical trials. They are run every year. In the United States, it's managed by the FDA, and they cost many tens of millions of dollars. It's like phase 3 clinical trials for different therapeutic areas. You can see the numbers. What is happening here? Well, this is a big stochastic control system, if you will, in which drugs candidates are coming in, and they're being tested to see if they should go to market. Do they help people? All right, so it's a stochastic control problem. And the people at the FDA are mostly statisticians, and they're good statisticians. And so they design protocols that are optimal statistical protocols. All right, so here's an example. So let's suppose I have a drug which is either bad or good, and no one knows a priori. Some person in Genentech designed some new protein, they wiggled something, and here's a new drug. Is it good or bad? All right, well now bad here means it doesn't do anything. It's like sugar. Bad doesn't mean it hurts people, because they do test for that. Okay, so internally it's not hurting people, but maybe it's just not effective. In fact, most drugs are not effective. Okay, no one knows that. But the FDA designs a statistical hypothesis to see that if the drug happens to be bad, the probability of approval is 0.05 or less. That's called the type 1 error. So they control the type 1 error. And moreover, if it's actually a good drug, the probability of approving it is 0.8. That's called the power. And the numbers are even a little more stringent than that, but they do this very, very well. Okay, and so that's how vaccines are done, and so on. And you have to get large numbers of people to do these A/B tests and get rid of the confounders and all that. So it's done really, really well. That's great. But is there a problem? Yeah, there's a big problem. So consider 2 cases. One in which there's a small profit to be made. It cost you $20 million to run the trial. That's kind of typical, as we saw on the previous page. And if you're approved, maybe you make $200 million for like a year. All right, that's a small niche drug, right? Now, the CEO can do this calculation right here. She can sit down and say, well, if the drug is counterfactually actually not effective, which I don't know, but let's just imagine for a moment my new drug is actually not effective. If that's true, what's my expected profit? And she will find that it will be, in this case with all those numbers, minus 10 million. So she looks at the number and she says to the bioinformaticians in the company, do not send any candidates to the FDA unless you're really quite convinced they're really good. All right, what does it mean to be quite convinced they're really good? Well, they didn't do a clinical trial. They don't really know, but they know a little bit. They have some internal information. Okay? Maybe they did a little internal testing. They know what engineers worked on it. They know something about the protein, et cetera, et cetera. All right, so that's that situation. If that were true, then the drug companies are mostly sending good candidates to the FDA, who's mostly doing good statistics, and most of the drugs we get on the market are really, really good. That would be great. But really, the reality is more like this, that it costs $20 million to run the trial, and if you're approved, you would make $2 billion. It's more like ibuprofen or something. And under that calculation, the CEO can do the same calculation, and she will find the expected profit, even if the drug is not any good, which she doesn't know, but she imagines maybe, is 80 million. Now she goes to all the engineers in the company and says, send as many candidates into the FDA as you can, because we'll have some false positives. They'll go on the market, and we'll make some money for a little while, and then of course we'll just be displaced in a couple of years when something better comes along, but we'll make we'll make huge amounts of money, 2 billion. This is what's happening all the time. Okay, our drug market is full of drugs which are not effective. All right, so how do you fix this? All right, well, first of all, you need to think not just like a statistician, you need to think like an economist. So here's the economist's view of this world. This is not what the FDA is doing, but the FDA should be thought of as a principal, and the drug companies should be thought of as an agent. And in economics language, there's an information asymmetry between the two. The principal wants to get some job done, all right? They don't have all the knowledge, so they turn to agents who have more knowledge, all right, to help them. And then they try to incentivize the agents to play fair. The agents now know something, and they're not just willing to hand that knowledge over to the principal because they lose competitive value, and they will not get a good price for their product. So they hide this. And that's just like someone going onto the airline. I'm walking up to the airline, and they would love to know how much I'm willing to pay for that airplane seat. If I'm really going to San Francisco tomorrow, I'm willing to pay $2,000 because I really want to get home. And if they knew that, they would charge me $2,000. Okay, so I hide that information so that they offer me a fare that's much more reasonable. Okay. All right, same thing here. These people are going to hide all their internal information so they'll get good licensing terms for if their drug happens to be approved. All right, so it is literally a contract theory problem. And so here's what we think is the right way to approach the problem. We call these statistical contracts. And I'm not going to get into details here, but basically this is what a contract looks like. An agent opts in or not. If they don't opt into this, they just walk away and no harm is done. If they opt in, they pay a reservation price R. They then choose a payout function F from a menu that we design. That's like economy class, business class, what are the services? The licensing terms and all that. All right, we design that menu. Then, so that's kind of classical contract theory. Line 3 is what's new. A statistical trial is run that generates a random variable Z coming from nature, coming from the true theta. We don't know, no one knows theta, but nature does. When you run a clinical trial, nature is using the truth. All right, so we get a random variable Z, which is the clinical trial. Then we get our payoffs, and everything is done. All right? Yep.
Is the theta that nature has the same as the theta that you assume the agent has?
The agent doesn't have theta. That's our model parameter, but the theta would tell us it's a good drug or a bad drug. No one on both sides knows that.
So what's meant by agent's private information is theta at the very top?
We denote the agent's private information as theta. Yeah, that's a random variable.
Okay.
Yeah, it's not known by, yeah, thank you. I should have put the random quantity.
Okay.
Yeah.
So it's like theta hat. There.
Theta hat.
Their estimate of...
Well, yeah, that's right. That's right. Yeah, good question. We could pick it offline and talk a little bit more about levels of knowledge you can have of various kind of quantities. That's right. But nature definitely knows it, and that theta is nature's theta.
But ultimately, it's going to be adversarial, right? And the agent is going to try to choose from the menu.
That's right.
Based on their theta hat.
Based on their knowledge internally, they'll get the best deal they can, and their best deal may be pretending to be there's something they're not.
Yeah.
Like if I'm a business class person, I might pretend to be economy class because whatever. So the payoffs, the agent gets the payoff depending on the terms of the agreement, and then the principal, the FDA, gets a payoff. They have to pay that amount, so they lose that. Plus, it depends on the true theta, because after a few years, the FDA will look bad or look good if they're doing a good job of regulating or not. All right, so think of this as a regulatory model for AI, if you will, for statistical decision making at scale. Okay, and it's not the regulatory model that's currently being used. All right, I'm going to try to finish in a couple of minutes. Well, not a couple. I'm going to do, till 5, right? Is that correct? Okay. All right, so what's the mathematics that happens at this point? Well, you've written down a well-defined mathematical object, a statistical contract. You can ask now, what is the overall utility? What's the revenue? What's the social welfare? You can calculate those quantities. You can lower bound them and upper bound them, and you can develop optimal algorithms and so on. So we did that. And the first thing you have to do in any of these analyses, and for the statisticians in the room, this is what you have to do that's new, that makes you into an economics statistician, is you have to say, what does it mean to be incentive aligned? Well, under the null hypothesis, that's theta 0, that the drug is actually not effective. Under that null hypothesis, your expected cost minus your reservation price is negative. Okay, otherwise, you would just be, the FDA would be losing money for no good reason. All right, so that's incentive alignment. Taking a p less than 0.05 threshold is not incentive aligned. We can prove that. All right, so are there incentive aligned contracts? And there are, when we have now an if and only if theorem. A contract is incentive aligned if and only if all payoff functions are what are known as e-values. What's an e-value? You all know what a p-value is. A p-value is the probability under the null hypothesis of being more extreme than the observed data. As you may know, p-values don't behave very well. In multiple studies, you can't combine them. You can't stop an experiment and look at the p-value. There's lots of problems with them. E-values fix some of those problems. They are random variables whose expectation, they're non-negative random variables whose expectation under the null is less than or equal to 1. So think of them as evidenced against the null. If they happen to be much larger than 1, it's strong evidence against the null, otherwise not. And in general, these are non-negative supermartingales. Okay? So you can stop them, you can combine them at all. Anyway, that's the statistics side. The new ingredient is that we've shown that those are in one-to-one correspondence with incentive-aligned statistical contracts. So it's a link between economics theory at the base and statistical theory at the base. All right, so from that, we can start going off into real world problems. And we've done this now for federated learning and several others. You'll see papers on my website about this. We have now a bunch of papers using statistical contract theory to design contracts for all kinds of real world problems. Okay, because we now know the class that's all these e-values, and we write down the appropriate e-values for the problem, and we've now designed a statistical contract. Okay, I'm going to skip this next little section. Just let me introduce the title to you and introduce Lydia and Horia, who are students with me. Lydia is now a professor at Princeton. This is another little project that brought together a learning idea and an economics idea. In learning, it was the idea of a multi-arm bandit, which probably many of you know about. I'm trying to find the optimal action among a set of actions by trying them out. Matching markets, there's Nobel Prizes for it. I've got colleges and people, and I'm trying to match who wants to go where. And if you just look at the multi-arm bandit problem, it's about finding what's the best arm under uncertainty. And if you look at the matching market problem, it's trying to link people on two sides of a market. So now you can ask, what if I put the two together? And I've got, on one side, agents trying to find the optimal action, but there are competing agents. And if they both make the same choice, only one of them gets the reward. There's a conflict. That's the congestion model I was alluding to earlier. And now you can write down what's the regret, and you can find the optimal regret, and you can find algorithms that achieve it, and so on and so forth. So we did all that in these papers. And the interesting problem that comes up is, does competition help you or hurt you in terms of regret? Okay. And the answer is, so you might think it would hurt you. If I pick the middle arm, because I'm the human, I like the middle arm, it looks really very good for me. I love it. But you like the middle arm too. And every time you pick it, the arm seems to prefer you and gives you the reward and not me. Now I say, I should explore more than I otherwise would. I should look at some other arms because I'm not going to get this arm because you're in the game. Competition seems to be hurting me. And the answer is competition does not hurt you in the actual regret, in the time decay of regret. It hurts you only in the constant. So there's a mathematical result there. All right, my last few minutes, I'm going to turn to this idea. So this is about uncertainty quantification in contexts where we've got multiple collaborating agents. One agent's going to provide a lot of knowledge, and the other agent is going to use that knowledge for some task. All right, so first of all, these are all my colleagues. They were all at Berkeley until very recently. Now, Stephen's gone to MIT, and Tiana's gone to Stanford, and Clara's gone to Genentech, and then now Anastasia's is still with me. Okay, so the setting here is the one that I've kind of alluded to earlier in the talk. We've got this powerful entity out there, it's called DeepMind in this case, that designed something called AlphaFold. It predicts proteins better than anything out there. It's fantastic. Even better than David Baker here at University of Washington. Question is, how do you use that in society? Right? Do you just plug it in? Is it just making everything better? Well, first of all, the numbers are quite compelling. We have hundreds of thousands of amino acid sequences that we know their crystal structure. And that has driven huge amounts of biology, drug discovery, and so on. But with AlphaFold, suddenly we have hundreds of millions of sequences that we predict their structure. And the predictions are the best we've ever had. They're really quite good. So can't we just throw away science and plug in things like AlphaFold? All right, so here's an example. This was a study done in 2004 where people were asking a very important question. Is there a relation between intrinsic disorder of proteins and phosphorylation? Proteins like to fold, but occasionally there's like little strands that don't fold, and that's because of quantum fluctuations. And those strands are important. It turns out if you make multiple strands and put them together, you can start to form grills, and you can put those in membranes and you can control things. So it turned out to be important. That wasn't known then, and these people did a hypothesis test using all of the 10,000 structures that were known at the time. And their hypothesis test just took a likelihood ratio and compared it. If it was 1, no effect. If it was bigger than 1, there was an effect. They didn't have enough data to make a decision. The confidence interval included 1. All right. These people came along in 2022 and said, well, we got AlphaFold. Forget using experimental data. Let's just use AlphaFold. Okay. Why not? We got 200 million of them. So they plugged them in and did the exact same hypothesis testing machinery and came up with a confidence interval. And it does not cover 1. It's quite bigger than 1. And so they said, well, we can conclude that the effect is real, finally. All right. Here is the problem. First of all, one problem is this is being done across all kinds of areas in science. You pick up Science or Nature recently, You will find papers that do this for other domains, like, evolutionary access, electricity access, regulatory DNA, so on, all kinds of problems. And here is the problem. This is maybe my last contentful slide. Okay, we took all the AlphaFold output, and we redid the whole experiment. We held out half of the data to get a ground truth on it, and then we did the experiment on the other half. The ground truth for this problem turns out to be a likelihood ratio of a little bit bigger than 2. So there actually really is an effect, it seems like, and we kind of know that. Here's the confidence interval from using AlphaFold predictions. It's tiny. That's good because we had a huge amount of data. We're extremely confident, but it's not even remotely covering the truth. Now here it doesn't matter because it doesn't cover 1. So you're rejecting the null hypothesis. You're making the correct decision, it seems like. So that's good, but you're not doing it on a very good basis. That seems a little worrisome. So you might go to a statistician and say, is this a good way to do science? They say, wait a minute, this is not good at all. You're not covering the truth. So they would say, well, let's just look at what we got for real protein data. Forget AlphaFold and go back to what we got. We got now 100,000 rather than 10,000. That gives you the gray confidence interval, classical statistician's confidence interval. It does cover the truth, as it provably will, but it also covers 1, so we still can't make any decision. That seems bad. So those two options seem bad. As you might imagine, we're proposing there's something in the middle. We call this prediction-powered inference, which is a new way to get confidence intervals that get the best of both worlds. They use information from this, but they also use statistical principles to debias it and actually get coverage at the expense of a slightly larger confidence interval, but an honest one. Just very briefly, details are on the web. This looks a little bit like what's called semi-supervised learning. It's not, but it has some labeled data where you have not only predictions, but you have the ground truth, and a lot of unlabeled data where you have predictions and you don't have the ground truth. And from all that machinery, we're taking, we're getting a confidence interval and we're unbiasing that confidence interval. Semi-supervised learning tries to take unlabeled data and improve the predictor. The predictor's AlphaFold, we're leaving that alone. We're trying to take the output of that and improve the confidence interval. Different problem. I just want to show you a couple of other examples. This is for a gene expression problem. Here you can see the AlphaFold type. It's not AlphaFold anymore, but some machine learning model is pretty good. Still didn't cover the truth though. But you can see the green thing is really, really thin. That reflects the fact that the model is pretty good. Okay, but still, we cover the truth. Here's a great example. This is something from the California census. It's about a logistic regression coefficient and predicting about something about health insurance. Look how bad the machine learning prediction is. It's completely terrible, but it's extremely sure of itself. Do you know people like that? All right. Now, our new interval covers the truth, but it's pretty big. That's because we're being honest. The model is so bad that we don't expect to get much reduction in our confidence interval. All right. By the way, why does this happen for AlphaFold? AlphaFold is so good. So I don't have a picture there, but for intrinsic disorder, so we put some proteins after the fact in that had a lot of intrinsic disorder into AlphaFold, and it made a lot of mistakes on those. Nobody knew. It just didn't happen to have a lot of those in its training data, so it folded it all up and didn't use this. Oops. But the fact is we found this in all kinds of problems, that the models maybe make lots of predictions, overall accuracy is high, but on a particular hypothesis you might care about, it might be bad. You don't know. This in one slide is how we do it. I'm running out of energy, so I don't know. I'll try to explain it quickly here, and then I'm going to finish. I'm a statistician, so I like to start. A frequent statistician starts with there's a truth out there that God knows. Let's call it theta star. There's the predictor, theta of f, which is DeepMind. Okay, that's theta of f if DeepMind could see all possible proteins. It's the population quantity of DeepMind. DeepMind is biased because it didn't have good data. Right? We don't know that bias. That's a population quantity. That's the supreme being knows that, but we don't know that. But we're statisticians, so we gather data, that's our labeled data, to estimate the bias. So estimating bias is known in statistics, and what's usually done is you debias an estimator. You take a bias estimator, you debias it. We're not doing that. We're taking a confidence interval on the bias, right? And then we're using all the values inside that confidence interval to do the debiasing of the original confidence interval. That's how we convert one confidence interval into a better confidence interval. It's all at the level of confidence intervals and not at the level of point predictions. All right, so we estimate, we call it the rectifier, the difference between that. We get a confidence interval for the rectifier. Then we take all the rectification possibilities and we pump the estimate from DeepMind through that to get a confidence interval for all of the corrected predictions. All right, it's actually very, very simple. And I think on that slide, if you care, you can actually see a proof of it working. And here's the actual proof at the bottom. But you can see that you kind of add and subtract something and you kind of use some standard statistics, concentration inequality kind of ideas. Okay, so I had that slide up there earlier, and I'm going to just leave that up there to maybe trigger further discussion, but I'm done. Thank you.
So we're a little bit over on time, so anyone, of course, if you have somewhere to be, please feel free to leave, but we can field a few questions. I imagine there's a lot of interest. Yeah.
So for the prediction powered inference, is it reasonable to think of that as being conceptually related to like conformal prediction?
Nope.
Or
It's a reason to think that, but it's not.
Okay.
So since you know what conformal prediction is, and probably no one else is, and I'm not going to try.
Okay.
But we have a whole section in the paper that says that. So just a little bit of sociological history here. This is the first time in 3 decades that I sent a paper to Science.
Okay.
Because you're supposed to send papers to Science when you want to have a big impact. That's what my biology faculty colleagues do. But I've done it a couple of times. When you send a paper to Science like one of us, a mathematician, they reject it immediately.
Yep.
Okay. So we thought, this is a good paper. This has an impact on scientists, how science should be done. We're not trying to sell anything particular. We're just trying to fix science. Let's just give it a shot. So we send it in, and a day later they say, no, reject. So then I called up my biology colleague, and I said, how do you guys live? This is terrible. They didn't even look at the paper. Give me a break. And they said, well, they sent it out to an expert. And what does that mean? Okay. They said, here's what you really do, Mike. What you do is then you send a hotly worded email saying, how could you possibly do this to my life's work? I'm a big shot, you ridiculous person, you. So I could never imagine writing such an email. So I just told my colleagues, no, I'm not going to do it. We'll go. But then I drank too much coffee one morning. And I wrote such an email. I couldn't believe I wrote it and I sent it. 3 hours later, they said, yeah, we'll take it out for review. And then it went in and got great reviews. And this morning it's been published in Science. So anyway, you'll see in that paper, one of the things the reviewers, it was a great process. The reviewers were very harsh and said, you need to add a lot. You need to add a lot of code. You better have a GitHub repo that does it with lots of comments. We did all that. We have now a beautiful, it's much better. One of the things they said is, isn't this just conformal prediction? So we wrote a whole section telling them why it's not. But thank you.
Any other questions?
Yeah.
So to propagate the confidence intervals
Yeah.
to complicated algorithms like AlphaFold, do you use something like automatic differentiation?
Yes, and that's also used in conformal. In fact, as you may know, the whole secret of neural nets is really automatic differentiation. That's why they're so successful. And so that has now become one of the things you can hold on to. You can take a complicated system of almost any kind. It has to be a neural net. It could be a differential equation. It could be all kinds of things. And you can run automatic differentiation, and you can grab a gradient. And if you saw on that last slide that I kind of skipped a bit quickly, it was all based on gradients. So if you can give me gradients, I'm good to go. Yeah.
Here's some of those emails for me, and I'll put your name on the paper.
Yeah, absolutely. No, I really hate it. I tell this story. I kind of hate to tell it. It sounds a little pompous in some level, but it's true. There's a little bit of that still in science, and the poor biologists have to live in that world, and they hate it, and I kind of hate it too. And I decided not to resist, partly because I have 4 young co-authors who I think their career will be helped by this, so why not? But it kind of triggers the desire in me to break the system. When I was a young professor, there was a journal called the Machine Learning Journal, and you had to, it was cost you like $2,000 a year to subscribe, and all the libraries are paid huge sums, and they were doing none of the work. So we started a brand new journal called the Journal of Machine Learning, and we wrote a whole diatribe against how horrible they were, and they still are. And that journal took off, and it's been a huge success. So I really don't believe in this model at all. That said, a lot of our more mathematical fields, we don't have a broadcast channel. We don't have a way of saying we got a cool idea. And so, science is not the best answer, but we've got to find something. As a statistician, I can publish papers in analysis statistics. No one in this room, if you're not a statistician, will ever read it. And similarly for my optimization work. So we need a broadcast channel.
How do we set up a market to do this?
Exactly. You're thinking in the right way. It's exactly about incentives. In fact, yesterday someone was asking me, isn't the real problem of the modern internet world and social networks and all that, it's not economic issues and all that. It's just people are jerks. There's terrible people out there. And I first of all, I resist that. I don't think that's true. But I think that if there's no incentive to do otherwise, not even a tiny little bit, the bad side will come out. If there's a tiny little incentive, they'll embrace that and they'll go and do the right thing. They want to do the right thing. But they need a tiny little incentive. And sometimes it can be very tiny. In our systems, the people who design these social networks and these music systems and all that just thought nothing about incentives, not even caring, not understanding. And I think that people will not be so bad if there's a little bit of more incentive. We're incentivized to stop at a red light. We should blow through the damn red light if we want to get there. But we know people don't do that because, a tiny bit of incentive. Yeah.
This is maybe an elementary question. With the source code of ML, how do you establish a ground truth or an evaluation framework?
Great question. It's not a naive question. It's one of the questions of the era. Okay, so in that big thing there, we did big Monte Carlo experiments. We took the whole big data set and we took half and pretended that we're in a world where we're the supreme being, that's the truth. And we threw that away and then we used that over here. We're sort of assuming that things are the same in these two sides. Right? So we're doing a typical kind of thing for a applied mathematician. You make a world in which it's a rich world, but you simulate. Right? And going forward, that's not going to be enough. We got to get better simulators, right? So the vision people, they did have a big success with natural language and vision because we had all the data. People gathered huge, vast corpora of real images, and that triggered a lot of progress. We don't have so much of that in this side of the field. We can't just do lots of drug discovery by, trying them out willy-nilly, right? So a lot of simulators are going to have to be done, and that's going to take maybe 5-10 years. Let me just say that that's not new. Boeing is sponsoring this thing right here. You know why our airplanes are so safe? It's not because they tried out lots of airplanes in an A/B test and see which ones crashed and which ones didn't. They did huge numbers of simulators. And they tried various control laws in that simulator and this simulator and simulator. They spent huge amounts of energy and time. And so I think a lot of us don't realize that we're supposed to just prove theorems and write software, aren't we? No, you're supposed to validate and try them out. And you don't have the data, we'll build a really good simulator. It's not a fake one that does it. So that's a really important question. And I don't know how to incentivize, a young professor to spend all their time writing a big simulator. Where are they going to get their career path there? But I think that has got to be thought about. It's really going to be important. I mean, if we had simulated some of these things with social networks, we might have seen some of the terrible things that came out of them. Thank you.
All right, maybe time for one last question.
Yeah.
Like classical microeconomics, most of their matching problems were kind of combinatorial optimization.
Yeah.
And I think the method you introduced today is most a convex optimization problem. So how did you convert it to combinatorial?
Yeah, another really great question. So I'm not going to be able to just slam dunk answer on that one. But, economists were pretty good about algorithms. These matching algorithms are actually not, NP hard. A lot of them are actually, they got nice algorithms. These were smart algorithmic people. They did make a lot of assumptions, though. And a lot of this kind of, humans are super rational kind of assumptions went into this. One of the advantages here, it's not quite answering your question, but I'll get back to it. One of the advantages here, instead of just writing down various curves of various kinds, utilities and all that, we're using data. And so the behavioral economics is already sitting in the data. It's behavior. And so when we fit a curve and put it in our systems, we're getting a little of the advantages of the behavioral. We're moving away from classical economics there. All right. Now that said, when economists write down these models and we condition them with data, we still might have a hard combinatorial problem to solve. I kind of hope we do, because it should be kind of matching. But then we have all of these techniques of Lagrangian relaxations and blah, blah, blah that really work at hard scale that we'll be able to apply there. So I have pretty high hopes for that.
But then the solutions or the equilibrium with the method that you introduced, did you actually prove that the solutions are stable or?
Oh, in some cases, we're able to prove that the equilibrium, we come within an epsilon of an equilibrium. Mostly, I should say, we're not doing Nash equilibria. Those are not such good ones behaviorally. And we're mostly working on these sequential settings where it's Stackelberg equilibria. So it's a richer class. And we're also using correlated equilibria, which are a little bit easier to find, and our algorithms will find that. we have a bunch of papers I didn't talk about that on that. That said, these are one of the big open challenges of the era. In a lot of problems there, you can maybe prove there are equilibria, but there are many of them. Which ones are good ones? How do you start the system up so it tends to find a good one? How do you say stable, even though, bad things start to happen? And again, this is not brand new thinking, but it's just that no one really solved or thought to solve the problems. In this new era, they become much more relevant. And it's really, as I said, it's not just about equilibria. It's about updating and staying healthy, which is maybe close to an equilibrium, but not right at it. All right, thank you, everyone.